does it mean to prove something in mathematics? A math proof is a really precise logical argument. You start with a bunch of axioms or principles and use rigorous deduction to reach a conclusion. That conclusion is then a proven math fact. Here's a great example. You can cover an 8x8 checkerboard with dominoes like this. But what if we take away these two corners? You can't cover it with dominoes. Why not? What's the proof? Pause to give it a try yourself. Okay, each domino covers one black and one white square. Since we removed two white squares, there are an uneven number of white and black squares. It can't work. What we just used is the first and most important tool in our mathematical proof toolbox, logic. Next problem. Take a stick of length 1 and randomly break it twice, so it's in 3 pieces. What's the probability those form a triangle? Pause here to think about the answer. The triangle inequality is a commonly cited fact about triangles. The sum of the lengths of any two sides is bigger than the length of the third side. Actually, that's maybe the most important tool in the mathematical toolbox, relying on previously proved results. The triangle inequality implies that the 3 broken pieces will form a triangle if and only if all 3 pieces, left, center, and right, are shorter than 1/2. Here, the center is too long to form a triangle, but here it works. So what's the probability that all 3 pieces are smaller than 1/2? To find out, draw an equilateral triangle, so the bottom side is the stick. Make 2 breaks on the stick and draw a dot where the 2 breaks form a smaller equilateral triangle, like this. We've associated each possible way of breaking the stick in 3 pieces with a point inside the triangle. This is a bijection, an extremely useful math tool that we talked about at length in our hierarchy of infinities episode. Bijections are a way of pairing objects in one set with objects in another set in order to compare them. In this case, we've paired up all the ways to break the stick with all the points in the triangle. Here's the key observation. If the right piece is too big, our point ends up here. If the center piece is too big, it ends up here. If the left piece is too big, it ends up here. But if all 3 pieces are smaller than 1/2, it ends up here. The middle is the good region, and it's 1/4 of the entire triangle. So 1/4 of the time, the break lands in the good region, and we have a triangle. Speaking of bijections, here's another great math fact that can be proved using a bijection. The sum of the natural numbers from 1 to n-1 is n choose 2. What do I mean by n choose 2? If there are n kittens, then there are n choose 2 ways to select a pair of kittens. For example, 4 choose 2 is 6. There are 6 distinct pairs selected from 4 kittens. To demonstrate the equality concretely, let's say n equals 7. But notice that, importantly, the proof works for any n. First, draw a pyramid of dots with 6 dots at the base. Notice that the number of blue dots is 1 plus 2 plus 3 plus 4 plus 5 plus 6. Now, draw a final row with 7 dots. Using this diagram, we can show that there is a bijection between pairs of points in the bottom row, which represents 7 choose 2, and the points in the blue pyramid, which represent the sum from 1 to 6. Any 2 points on the bottom row are paired up with the point in the pyramid where the diagonal lines extending from them meet. The fact that we can make a correspondence, aka a bijection, between the pairs of points on the bottom row and the dots in the top pyramid means they must be equal in number. Roger Nelsen's book, Proofs Without Words, contains a bunch of visual proofs, from the ancient classics to the wildly more complicated and modern ones. I particularly like this simple one. The sum of the odd integers from 1 to 2n-1 is n squared. So, for example, 1 plus 3 plus 5 plus 7 plus 9 plus 11 plus 13 plus 15 is 8 squared, or 64. Actually, There's a special math tool called induction that's often used to prove facts like this, which hold for all natural numbers n. To use induction, you first prove the theorem holds for n equals 1. Then you show that if it holds for n, then it also holds for n plus 1. It's like saying, my ladder has a bottom rung, and every rung has one above it. Therefore, we can climb as high as we want. Here's an example. A 2 to the n by 2 to the n chessboard with one square missing can always be covered by L-shaped tiles, like this. First, we show it holds when n equals 1. These 4 pictures show that any 2 by 2 chessboard with one square missing can be covered by an L-shaped tile. Now, assume all 2 to the n by 2 to the n boards have this property. Here's a 2 to the n plus 1 by 2 to the n plus 1 board with one square missing. Let's try to prove it also can be covered. Break it into 4 equal pieces. One has a missing square. Place an L-shaped tile over the other 3 like this. Now, you have 4 2 to the n by 2 to the n boards, each with one square missing. We already know all of them can be covered by L-shaped tiles, so our whole board can. We just used 5 classic tools that show up in mathematical proofs: rigorous logic, bijections, citing previous math results, pictures, and induction. Next episode, we'll add a few new tools, but these essentials will take you far. What's your favorite proof using these tools? Let us know in the comments. See you next time on Infinite Series. Hello! I'm going to respond to some comments on our Infinite Chess episode. So, MeloDeath says, how is it possible to make an infinite move on an infinite board? Well, good question. It's not, really. You can make an arbitrarily large, but finite move. So, you can move as far as you want. You could move a rook 10 spaces, or a million spaces, or a Graham's number of spaces. But you're right that it doesn't really make sense to move it infinitely far. TheDruidKing asks, why are there 3 black rooks? Well, part of the setup of infinite chess is that you can put any number of any of the pieces on the board. So you could put 3 rooks, you could put 10 rooks, you could put infinitely many rooks. You could fill all of the squares with rooks. It'd just be kind of a boring game if they were all filled with rooks. Joel Hampkins does actually have some examples of chess games that have really interesting results and have infinitely many pieces on them. Rayfangrui points out that the concept we're using is not the same as mate and n in chess. That's true. It's similar but different. We defined the doomsday clock a little differently than you define mate and n. If you say mate and 2, you mean that the winning player has to make 2 more moves. You're not counting the moves of the losing player. To define the doomsday clock and to make all the infinity stuff work out, we need to count the moves of both players. So we need to define our doomsday clock a little different than chess players define mate and n. So thanks for reminding me to put that clarification in. Okay, have a great week.